All right, so I'm gonna talk about some new results related to an old modeling framework that I've been studying for maybe 10 years now. And yeah, so domination is going to be a big part of this talk. All right, so some motivating ideas. So I realize this is the last talk, right? So thanks for staying till the end. Motivating ideas for this. So first, I think, there's a sort of new, not so new, but kind of idea that's taken on more seriousness lately, which is the brain is a dynamical system. People also say the brain is a computer, so you can take your pick. But one of the things that I've been really interested in, and people in my group, my collaborators have been really interested in, is how does connectivity shape the dynamics, right? So neural networks are different from other kinds of cellular networks in that there's very specific connectivity and it's very asymmetric. And so one of the kind of motivating ideas is that if we study like attractor neural networks or artificial neural networks, we can generate hypotheses about the dynamic meaning or role of various network motifs. So there's all this work going on right now in connectomics, which many of you might be aware of actually trying to figure out the wiring. How are cells connected to each other? What's the underlying graph? And it's kind of a very heavily annotated graph. And then the question that arises is, what do these connectivity patterns mean? How are they going to shape the dynamics? And then sort of on the forward engineering side, it's kind of interesting to try to see, can these motifs be composed as sort of dynamic building blocks and therefore give us a sort of toy model where we can explore and generate ideas and new mechanistic hypotheses about how dynamics in the brain is actually working. The other sort of idea that we're going to come to towards the end is that a single network is really many networks. So in other words, as you modulate certain parameters, in this case we're going to modulate kind of like an external inhibition parameter, you can actually reveal sort of subnetwork structure that is gone in the entire network. Okay, so plan of the talk, I'm going to start with like a brief crash course into threshold linear networks, CTLNs, which you already heard about a little bit from Juliana yesterday, and the generalization. And then I'm going to talk about why we care about these networks, what is the sort of mathematical tractability that we get. Then we're finally going to get to domination, which I'm extra excited about, and then the inhibitory control. I want to highlight this EI-TLNs that's coming later. So a lot of people ask, like, the framework feels like it's all about inhibitory networks, but in fact, there is a mapping to a genuine excitatory inhibitory network, but I'm not going to sort of reveal that until later. So for now, just sort of trust that you can really think about the nodes as excitatory neurons living in a sea of inhibition. Just kind of, suspend your disbelief for a moment, and I'll try to convince you towards the end that that's a reasonable way to think about it. Okay, so threshold linear networks. So it's not a single model, right? It's a whole modeling framework. And I really think of these as quite analogous to linear systems of ODEs. So the threshold linear dynamics, it's a firing rate model. The X's are typically thought of as firing rates of single neurons or of subpopulations of neurons. And you have a connectivity matrix and some external drive. And then we choose this ReLU, the threshold nonlinearity. And the basic question, right? So the network is parameterized by the W matrix and the external B vector. So sort of assuming that's not changing in time, that gives you some network, and then of course B and W can change in time. But let's freeze them, and that gives us a particular TLN. And the basic question is, given W and B, what's going to happen, right? What are the network dynamics? What are the asymptotic dynamics? And this is on some level a wildly ambitious question. This is a high-dimensional, nonlinear dynamical system, but we have an example where we can solve that question, right? So if you had a linear system, we just drop that nonlinearity, then you have a linear system of ODEs, right? And linear algebra tells us everything. So that's a case where we do know the asymptotic behavior. You don't have to run simulations, you don't need AI or anything fancy, right? We teach this to undergrads, how to figure out the asymptotic behavior of a linear system of ODEs, basically looking at eigenvalues and eigenvectors of that matrix A, okay? So wouldn't it be awesome if we had such a strong theory in what I consider kind of the simplest nonlinear variant of that problem, right? And it could open up a lot of possibilities. Okay, so that's kind of what we're trying to do. Of course, we can't go to the full problem all at once, so instead we look at a subfamily of these threshold linear networks, and we look at a subfamily that's defined from a directed graph. So this is the first case that we studied in detail, the combinatorial threshold linear networks. Again, it's the same framework, right? I'm just picking W's to come from directed graphs in a special way. People have been studying these networks in computational neuroscience, I should say, for like decades, probably 40 years at least, the papers go back. And typically they've chosen symmetric W matrices. They've shown that these networks can encode stable fixed points, kind of like Hopfield networks. They've shown that you can get line attractors and ring attractors. I have a paper myself using them to get bump attractors to model hippocampal place cells from like more than 10 years ago. But typically that W matrix has been chosen to be symmetric, in which case you have kind of guaranteed convergence to stable fixed points, and they don't oscillate. So when W is symmetric, these guys don't oscillate, okay? So the approach here is to go the other extreme and really think about directed graphs and building the W matrix in a way that is going to be clearly asymmetric based on the asymmetry in the directed graph. So in other words, we have two, in this case, just two parameters, an epsilon and a delta. They don't have to be super small, by the way. They have to be positive, and epsilon has to be less than delta over delta plus 1. And the game here is that you're taking your graph, using it to build the W matrix, and the entries of the W matrix are keeping track of kind of weak versus strong inhibition. Okay, so you can think of these networks as sort of a generalization of winner-take-all networks. They're competitive, right? The neurons all inhibit each other, but some inhibit each other weakly and some strongly, okay? And that can be very asymmetric, right? So I can inhibit J strongly, but J can inhibit I weakly. And then you would get kind of flow of activity. All right, so this is kind of, so Juliana talked about these networks yesterday as well. And the cool thing about them is that they produce oscillations. They produce dynamic attractors, chaotic attractors, kind of all the nonlinear phenomena that you might hope to find in a modeling framework. The generalization to GC-TLNs, now all of a sudden I'm allowing every node to have its own epsilon delta parameters. So it's not quite the full generality of the n, sort of the n squared dimensional space of W matrices, but now we have two n parameters, okay? So this is also an important generalization that I'll talk about some more. But again, the idea is it's tracking weak and strong inhibition, and I really do think of the nodes as excitatory neurons, even though they're all inhibiting each other, okay? And the reason is because think of them as an excitatory network in a sea of inhibition. Like there's a global inhibition in the background that's bringing all the weights down, and so when you had an excitatory connection, like if J goes to I think of that as an excitatory connection, but then with the inhibition bringing it down, it becomes a weak inhibition. Okay, and critically, it's weaker than the neuron's self-inhibition through its own self-leak term. And that's very important because that's what's going to make the dynamics kind of flow along the arrows of the graph. Okay, and I will show you later how you can actually map this into an honest EI network where you actually would have positive weights where there's arrows and zeros where there's no arrow. Okay, so that's how I kind of think about the space of recurrent networks. We have all recurrent networks. This is not to scale. But we have TLNs. We have the competitive TLNs, where you have this sort of effective inhibition between every pair of neurons. We have the CTLNs. This is small family. But crucially, we get to sample the W space corresponding to different graphs, right? So on the one hand, it's constrained, but on the other hand, you're really taking very different points in the parameter space of all TLNs. Instead of perturbing, like random perturbations are out in some weak coupling limit, you're kind of taking big changes by changing the graph. And then the GC-TLNs are a generalization of that. And then people do still study heavily linear models, and so they're tiny, but still quite useful. Okay, so why do we like these networks? They have a lot of nice features. They display, as I was saying, rich nonlinear dynamics. I'll show you some examples. They're also mathematically tractable, so we can actually prove theorems that are useful connecting graph structure to the dynamics. And they also display, it's a situation where both stable and unstable fixed points play a critical role in shaping the dynamics. And so an important object for us is this FP of G. Okay, so this is like as a function of the graph, you can track supports, so subsets of neurons that support fixed points, whether stable or unstable. And that ends up encoding a lot of information about the network. So here's our first kind of non-trivial attractor that we get from these networks. So if we have a theorem. So early on, a lot of this work was kickstarted by a theorem that I have not cited here. I've actually cited the work that proves the existence of this limit cycle, which is not my work. But the theorem says that if G is an oriented graph with no sinks, so that means you have no bidirectional connections, okay, and all the nodes have at least one edge coming out of them, then you're guaranteed in the CTLN model to have a dynamical system with no stable fixed points, but bounded activity. Okay, so immediately we can go into networks and start playing with dynamic attractors because we're guaranteed not to converge to a stable fixed point. Okay, it's like the opposite of the classic Hopfield model result. And the smallest oriented graph with no sinks is the 3-cycle. And you see, like, so I've picked a couple of parameters, an epsilon and a delta. It doesn't matter too much how you pick them, but you'll see that once you set this up, it's the same TLN equations, but coming now from this graph, and you get this nice 3-cycle oscillation. Okay, so very basic, but it emerges immediately. And it's kind of interesting how the oscillation works, because these systems are actually piecewise linear. Okay, and we are forbidding fine-tuning, so you're not going to have eigenvalues that are like purely imaginary or anything like that. And so what's happening is that locally there's an unstable fixed point in this sort of central chamber, and as the behavior is basically spiraling out of that fixed point. But as you spiral out, you cross a hyperplane, and the hyperplanes are defined by setting the argument of the nonlinearity here to 0. Right? So there will be one for each equation, one for each neuron. And as you cross the hyperplane, you're now in a different linear system because you've set something to 0, right? And then you have a different, your trajectory keeps going, and then you come back into that central chamber, and every time you come back in, you spiral out, but you catch the spiral at an earlier spot when you come back in. I don't know how much sense that makes when you first see it, but it's like a very interesting way that the limit cycle emerges. And the existence, so we see this computationally very easily, but the sort of a mathematical proof of the existence of these limit cycles, not only for the 3-cycle, but for any n cycle, is in this nice paper by Horacio Rothstein and collaborators. Okay, so you might wonder in the GCTLN, where we were able to have more freedom on the parameters, how does that 3-cycle oscillation change? It's kind of interesting. So I just made a couple of examples here. So changing the parameters, very small here, but you can see that you can change the amplitude and the timing of the oscillation. But the oscillation is there, right? It's there for a very wide range of parameters, provided you're in one of these CTLN or GCTLN families. And here's a different one, right? So in this one, the green corresponding to neuron 2 got made really high, and the others are smaller. I can make one high. It can regulate it in different ways. It's really kind of interesting, and we haven't fully explored, what are all the different shapes that the oscillation can take. But you do have that freedom. I mean, these are all attractors, right? So they're very robust. It's not some fine-tuned, circular trajectory that required purely imaginary eigenvalues. Okay. We also get really exotic attractors. This is probably my favorite. Call it the Gaudi attractor because it reminds me of the architect from Barcelona. And here is just a simple, we call this the 5-star network. It's a tournament. It's a circulant tournament on 5 nodes, and it actually has 2 different attractors that emerge. This one up here, where the curves just seem like they're melting. And then the boring one, which is the one you expect, which is the limit cycle that just cycles around the outside of the graph. Okay, you can also get, very nice torus. And here's a 7-dimensional space is a quasi-periodic trajectory that emerges from another simple graph. So now it's like this opens up just a huge playground, right? So it's like pick your favorite graph and see what kind of dynamics does it have. And so we've played a lot with it. And one of the sort of central observations is that these attractors are really tightly related to the fixed points, to the unstable fixed points even. And so, for example, in this baby network, you have a sink at 4 and a 3-cycle 1, 2, 3, and we can actually predict with our theory that you're going to have exactly 2 attractors here, one corresponding to the 3-cycle and one to the sink. And you can see here in the state space, there's a third unstable fixed point that is not minimal. So Juliana talked a little bit about minimal versus non-minimal fixed points, and we mean minimal under inclusion. So a collection of neurons that fires at a fixed point and there's no smaller collection, right, that also fires at a fixed point is considered minimal. So here 4 and 1, 2, 3 are minimal fixed point supports and 1, 2, 3, 4 is not. And you can see that the attractors are corresponding to the minimal ones. You have one limit cycle and one stable. We also get, chaotic dynamics in the sense of like strange attractors, not ergodicity. And this is the first time we saw chaos. We call it baby chaos, this example. It's just 5 nodes, and there are 4 chaotic attractors. They look a lot like the Rossler attractor, actually, but you get 4 of them in one shot. Okay, so lots of fun. You can also think about graph automorphisms, and there are interesting consequences to having a symmetry of the graph that induces a symmetry of the vector field in the CTLN case, although not necessarily in the GCTLN case. And sometimes that results in synchronous firing. So here, this graph has an automorphism that sends 2 to 3, 3 to 4, and 4 to 2, right? It's like a cyclic permutation. And the corresponding limit cycle attractor has nodes 2, 3, and 4 synchronizing in the limit cycle. But it could also be that the symmetry acts on the set of attractors in a way that like exchanges attractors, right? So it's not that each individual attractor must respect the symmetry, but there's a group action on the set of attractors. And then here's a sort of interesting phenomenon we also discovered, which we call surprise symmetry. This is kind of the opposite of spontaneous symmetry breaking. So spontaneous symmetry breaking is when your equations have a symmetry, but your individual solutions, they pick some solution that doesn't respect the symmetry. It's only the space of solutions that does. Surprise symmetry is when we've broken the symmetry at the level of the equations, but it's still there at the level of the attractor. And that's because the attractor is only occupying a subset of the whole space. And so the symmetry is obviously holding there. Okay, and then just a lot of people ask about this, and it's good to settle once and for all that you can have many attractors of different kinds coexisting in the same network. Okay, so there's a lot of work in theoretical neuroscience where you have like some parameter and there's a fixed point regime and then a chaotic regime or a limit cycle regime as you move this parameter, and there's this illusion that these things cannot all coexist in the same network, but in fact they totally can. Okay, so you can play with this stuff yourself if you're curious, you want to play with these networks and explore the dynamics. We have nice code and some accompanying papers. Katie and I wrote a review paper, and it has an extended version in the notices a couple years ago that you can check out if you're curious. But now I just want to come back to sort of newer results and review quickly why we like these networks so much. So first, we like them because they're expressive. Right? You get lots of different kinds of attractors and limit cycles and so on, and this can be very useful for modeling brain rhythms and oscillations and other interesting things that are happening in the brain. And you saw some of that in Juliana's talk yesterday. But why do we care? Why do we like the threshold nonlinearity? I was watching the Wimbledon final a couple months ago. It was Sinner and Alcaraz. I don't know how many of you, did anyone watch the Wimbledon final? Right? After the French Open final, you kind of have to watch this one, right? And I'm watching it, it's like on the television at my friend's house, and suddenly I see the threshold nonlinear. So I took out my phone, and I was like, I gotta take a picture of this and use it in a talk, so there it is. But why do we care? We care because it actually turns the system into a piecewise linear system, right? So we get this patchwork of linear systems, and you have this accompanying hyperplane arrangement, and this really nice feature that you can index your fixed points by the support. There's at most one fixed point per chamber, and there's all kinds of like nice, elegant mathematics that goes along with it. And so we've done, we have, several papers that sort of detail how this all works. And, sort of early on, we came up with some nice technical results exploiting the piecewise linearity. Okay, so basically, if you're willing to do linear algebra with careful tracking of combinatorial things and the hyperplane arrangements and so on, you can get a lot of mileage out of this and really understand kind of the high dimensional nonlinear dynamics using the piecewise linear structure. And in particular, in the case of CTLNs, we have all these graph rules. So we were able to prove theorems relating directly the graph structure to the attractor structure. And so, again, there's a review paper on this, and I'm just going to show you maybe one graph rule before getting into the domination, just to see how it works. Okay? Actually, it's interesting. So there was a talk the other day, and I forget exactly which one it was, but somebody talked about regular graphs where every node has the same number of incoming edges, okay? So we also discovered that we can get mileage out of considering what we call uniform in-degree graphs, and those are graphs where every node has the same in-degree. And so one of the earliest graph rule theorems that we came up with was that if you look at an induced subgraph in your larger network and it's uniform in-degree, then the nodes in that subgraph, which sigma is a subset of nodes, it's a subset of neurons, it will support a fixed point, so it'll be in this FP of G set, if and only if no node outside the subgraph receives two or more edges from the nodes in sigma, okay? So this is it's an if and only if statement, it's a very clean characterization, and we get this immediate corollary, right, for the cycles, which is that if you have a cycle embedded in your graph, then the fixed point, there's going to be a fixed point associated to the local subnetwork, and it's going to survive precisely when no node outside receives two or more edges in this case, because the cycle is uniform in degree 1. And so, for example, this is a graph that has three cycles. You see the 2, 5, 3, 1, 2, 5, and 1, 4, 5. Okay? But only 2 of them satisfy this property for fixed point survival. In fact, this one, the 1, 4, 5, there's a node 3, that receives 2 edges from it and kills the fixed point, okay, and also kills the accompanying limit cycle. So we're actually only getting 2 limit cycles corresponding to the other 2 3 cycles in this network, okay? So that's the kind of thing we can do, right? So we can prove theorems about how the fixed points relate to the graph, and then we have this heuristic, which is that we predict, it's not 100%, right? So this is a heuristic that when we have these minimal fixed points, they're going to correspond to attractors, and then we can go and find the attractors, and they're easy to find, okay? So this is just kind of a summary on some observations, but I'll sort of skip this for now. I encourage you, if you're curious about these networks, to read our review paper. Okay, so let's get to domination. So this is one really important graph property that we had seen maybe 5 years ago, actually published a version of it early on, and then came back to very recently, okay? So here's the original definition of domination, okay? So suppose you have, it's a property on the graph. Suppose you have 2 vertices, J and K. We say that K graphically dominates J if the following 2 conditions hold. Every other vertex, if it goes to J, it also has to go to K. That's condition 1. And moreover, J goes to K and K doesn't go back to J. Okay, so somehow K is receiving more inputs than J. It's receiving all the inputs that J is getting and maybe more. And also between them, you have this asymmetry where J goes to K and K doesn't go back to J. Okay? And if that relationship exists, we say that J is a dominated node. And if there's no such relationship in the graph, we say that the graph is domination free. Okay? So here's an example, just a graph on 7 nodes. And I just taught a summer school a few weeks ago in Norway, and I asked people to sort of find the domination relationships, but I won't do that here. Not as interactive of a talk setup. You can see 6 dominates 7. You can check those conditions, and also 4 dominates 3. Okay, so we have 2 of these relationships in the graph. And we had an old theorem, back more than 5 years old, from 2019, which said the following: if you have a domination relationship, then those 2 nodes can't participate in the same fixed point. Okay, so in some sense, the fixed points were like egalitarian, right? You can't have a node that dominates another and still have the sort of the balance that you need to be at a fixed point. And it doesn't matter if the fixed point is stable or unstable, right? It's ruled out. That support is ruled out if you have a domination relationship. And so in our example, the old theorem just told us, okay, whatever the fixed points are for these network, for a CTLN with this graph, you're not going to have any fixed points where 6 and 7 both appear, or where 3 and 4 both appear. Okay, we were pretty happy with that. It's a graph rule, right? It's it's something about the graph that's telling us, ruling out certain fixed points, and we published it along with a bunch of other work and moved on. Okay, so now this is like one of the weirdest things that's happened to me in my professional life. These are my children, okay, and the smaller one, about 1.5 years ago, he was 12, he's 14 now. He starts telling me this story about a discussion that he had with his brother on the beach on a family vacation. And he and his brother, Yuli, who's 4 years older, they had been talking about the rock, paper, scissors game. And, all kids, you guys know the game, right? You do rock, paper, and then you do like scissors or paper or whatever. And there's a relationship, and I've drawn it in the way that you might draw it in a game theory sort of setup. So paper beats rock, rock beats scissors, and scissors beats paper, okay? And so they had been playing this game, and they had wondered what happens if you add another choice, right? So they were like plastic, that always loses, okay? So if you add a 4th choice, they wanted to expand the game. They got bored with it, right? So let's add some choices. So if you add a choice that always loses, no one's ever gonna choose it, right? It's just gonna not be a strategy that anyone ever picks, and it drops out. But then they came up with this interesting alternative. It's like, what if you add a choice that wins some of the time and loses some of the time? Like bomb, okay? So they're like, bomb is gonna beat rock, and it's gonna beat scissors, but it's gonna lose to paper, okay? And so they had thought about this and maybe played the game a few times with adding bomb as an option. And they realized you would never choose rock anymore, okay? Because every time rock wins, bomb also wins, but bomb also beats rock, right? So there's no need to ever choose rock anymore, and rock would drop out, okay? So he's telling me this, and they were like he was really excited to share this because it's a non-trivial thought. It's like, you're never gonna choose it, it drops out. And he's telling me this whole story, he's like, you know what I mean, you know what I mean? I'm like, oh my goodness, yes, I know what you mean. Because bomb dominates rock, right? And they had sort of discovered that. They had discovered a domination relationship, and that then the dominated node, the dominated strategy, you would never pick. I got very excited and started showing him the graphs and everything, and then he was like, okay, Mom, whatever, lost interest. But this haunted me, right? Because of the dropout concept. So of course this is a game, this is like a totally different setup than our inhibitory neural networks. But this idea that the dominated node drops out, right? And we could never prove that with the fixed points, right? We knew that it couldn't coexist with its dominator, but we could never prove the dominated node fully dropped out. And so then I went back for 3 days. I was obsessed with this. I went back to the proofs, tried to clean. I had actually recently cleaned them up and written even simpler versions for this review paper. And so I delved back in, and I was like, could we have proven this? Could we have proven that the J node just totally disappears? And then I was able to prove it, right? So looking for this more specifically, I was able to prove a new result, which is that not only do none of the fixed points involve J and K, but actually J drops out. So in other words, the fixed points of the full network are identical to the fixed points of the reduced network when you remove the node. And this is the induced subgraph. So you remove the node and all the edges that it's involved in, okay? And here I'm just showing it at the, in this statement, I'm just showing it at the level of the supports, but it's actually the values of the fixed points are identical, right? So in other words, you take the fixed point from the smaller graph and pad it with a 0 on node J, and you get the fixed point from the larger graph. Okay, they really are the same fixed points, and we just hadn't realized we could prove this anymore. And the beauty about having this proof is that now with the dropout phenomena, you can iterate. So we couldn't do before. Now I can remove node J. So in this example, right, K dominates J. I remove node J, and now suddenly K becomes dominated. It wasn't dominated before in the larger network, but it's dominated now after I remove the first node. And I can keep going and get it all the way down to a smaller graph. And even going back to this old example, okay, so I have these dominated nodes, 7 and 3. When I can remove them, then the induced subgraph now has new nodes that are dominated, and I can iterate the application of the theorem and keep removing until I get all the way down to this 2-click. Okay? And so suddenly I can now tell you not only, you know, are J and K not involved in any fixed point, but I can actually reduce the network and tell you that all the fixed points of the big network are actually fixed points of this small network, which in this case is just a single stable fixed point supported on the 2 nodes 4 and 5. Of course, we worried, because, you know, as mathematicians do, we worry, does it matter what order you remove the nodes in? This actually was like the harder theorem to prove, I have to say. But did manage to also prove that no matter what order you remove the nodes in, you always get down to the same reduced graph. Okay, so this is very exciting. And in particular, we had for a long time this intuition that all the dynamics is happening where the fixed points lie, even if the fixed points are unstable. So somehow if the fixed points are all living in this subgraph with 4 and 5, that's where the dynamics should go. And so you could actually do the computational experiments and start with the large graph. And I haven't told, you know, MATLAB or whatever that I've reduced the graph. I'm just running I'm running the CTLN on the large graph, and I find the activity, you know, gets sucked into that stable fixed point every time. And these are GCTLNs actually. So it works. All of this stuff works for GCTLNs exactly the same. So the domination theorems hold in this larger family, okay? Also, if you have, you know, multiple fixed points in the reduced graph, you can converge to both of them. And even if you have sort of more interesting dynamic attractors in the reduction, again, the large network, the activity is like, it gets sucked in to the subgraph, okay? So this is incredibly powerful now, because not only do we know for sure that the fixed points are just the fixed points of the subnetwork, but we also have a lot of evidence and some conjectures about the vector field kind of sucking things into the subnetwork, okay? So we don't have, you know, we don't have like a global Lyapunov function or anything like that, but we have kind of some local variant of that. Okay, so this is really, I don't know how much I'm saying about this, but I just want to sort of emphasize that, like, part of what made this possible, in addition to this like random comment from my child, right, is that we made an effort to like really clean up our theorems, right? And so then when I went back, and it was like I could see more transparently, oh yeah, I really could, you know, do more, and I could generalize to GCTLNs as well, and prove the dropout phenomena. And so, and I'm just showing this, not, I mean, I'm not trying to like have you follow this really small text math, but the point is it fits on one slide, okay? So it's not hard once you kind of know what you're doing, but it's a lot of just analyzing the equations for the fixed points and being careful about the nonlinearity and various inequalities. It's all very elementary techniques, right? But you kind of have to know the big picture of where you're going with it. Yeah, and this is really, yeah, a situation where like there's no way we could have possibly checked this enough to feel like it's true if we hadn't been able to prove it. Okay, so now I want to like switch gears a little bit and start using this intuition about how the activity gets sucked in to the subgraph that is the reduction. Okay, so this is motivated kind of these new like fun building blocks that we're playing with right now in my group, which we call dominoes, because they do look kind of like dominoes, and also dominoes is like domination. And there's this cascading effect. So now here's the idea, right? So I've just shown you, this is actually the same graph I showed you in the example, 7 nodes, and it reduces down to these 2. So now we can think of the domination reduction as giving us a partition of the graph, right? It's the stuff that's going to end up getting peeled away by the domination reduction. That's the G omega part, and then the tau part is what you reduce to. Okay? But now imagine, and we're going to just call this the domino of the graph. We're going to sort of like, we know that these edges are set up in such a way that we're going to reduce to this one, but now we can just track the 2 induced subgraphs. So we're losing some information here, and we call that the domino. And what the theorems told us is that the fixed points of the full graph are supported on that tau piece, okay? And the conjecture is that the activity is going to flow towards that tau piece. So taking the conjecture seriously, now we can imagine, all right, here I converge to a 2-click, but I could have another piece of network where the 2-click reduces down to a node, like this. That's another like domino piece. And then I could have another piece where I have this network and it goes down, it takes a node, you can sort of imagine gluing that node into here, and then it reduces down to this pair, and so on. And so the idea is now we're gonna glue these subnetworks together in a way such that the tau piece of one gets glued into the omega piece of the next one, right? Remember, the omega is the one that the activity is going from omega to tau, right? But now I'm going to glue the tau of the first into the omega of the second and iterate like that and chain them together. And it's not so hard then to prove kind of theorem 3, which is that if you glue reducible graphs together in this sort of controlled fashion into a linear chain, then the fixed points of the full network are actually going to match the fixed points of the reduced piece of the final domino. Okay, so really at the level of the fixed points, it does all collapse to the final component. And the heuristic or the prediction is that the activity will also flow that way. Okay, and that's exactly, I sort of cut the examples up, but that's exactly what we see. If you like put these things together, you will see the activity completely flow to the last component. Now, this is the fun part. What happens if you wrap it around? Okay, so I've made my chain, but now I'm going to take the last piece and glue it into the first one, the omega part of the first one. Okay, now my whole domino strategy collapses because these nodes that were dominated up here that I could peel away and then iteratively reduce, they're no longer dominated if they're receiving inputs from another piece. Okay, and so the theorem goes away, and what ends up happening is you get fixed points that hit every component, okay, and activity that cycles around. So it's a way of building limit cycles. In fact, going back to the cyclic union construction that Juliana talked about yesterday that she used for the gates, this is in some ways a general framework where you get very similar kind of behavior. So here's an example where I've chained together a bunch of dominoes, and then the last piece I'm going to identify with the last node with the first node, so that it cyclically loops around. And so maybe I should show this first, but like what you're going to get is limit cycles that loop all the way around the network. And then we're going to play a game, and this is the inhibitory control, where we selectively inhibit nodes that are along the limit cycle. Okay, so let's get started. This is like a very instructive example. So we have this network, the last node is identified with the first one, and there's domination the domino setup has been used to make this. And what you see initially, I'm calling it like a resting state limit cycle, right? But the activity is just looping all the way around the network. And you can see this activity. You have this limit cycle. This is a grayscale. These are neurons on the axis, and you can see these sequences, and it just repeats, okay? And then as soon as I inhibit this node 16, So what do I mean by that? And so instead of stimulating it the same as I'm stimulating all the nodes, like this flat b equals 1, I'll just give it less. Okay, so it's like an inhibitory control signal. And you can see the suppression here of node 16. And then what happens is the activity, like the network doesn't really see it until it's looped back around into the neighborhood of 16. And then what happens when you do that is you actually subvert the domination relationship, which did depend on the external inputs all being equivalent, and you get stuck in this two-click. So suddenly that fixed point, which is not a fixed point of the full network because it had, it got killed by this node, when I inhibit that node a little bit, it's revealed as like a potential fixed point again, and your activity gets stuck there. And then you can release that, and you go back into the long limit cycle. And then you can inhibit other nodes and get it stuck up here. And this is now a 3-cycle. And so I'm getting stuck in this like 3-cycle oscillation, which is there. So I'm revealing these attractors that are kind of in the network, but have disappeared when everyone's getting the same input, right? So the picture is that you have this sort of ongoing oscillation, some kind of resting state oscillation, but then as you just touch a neuron a little bit, here or there, you just like inhibit a little bit, you get stuck. It's like a stop sign, and the traffic gets stuck, and then it's like whatever attractor was there gets revealed, and you're in this holding pattern. And then there's another fixed point that can be revealed. The cool thing is then when you release the inhibition, you go back, the sequence continues where it ended off. Okay, so it's like you put a stop sign, and then when you release it, it just keeps going. Okay, so you haven't lost your place in the sequence, even though you can stop for a really long period of time. Okay, so this is like, I'm not showing in this talk, data of this kind of phenomenon, but it's something that we've been thinking about in collaboration with some monkey electrophysiologists who have these tasks, and there's like a waiting period. And so there's a lot of things in here that have actually informed the way we're thinking about what's happening in these sort of motor cortex tasks. Okay, so as promised, these networks really can be thought of as excitatory inhibitory. So far, we've assumed this framework where it's a competition model and all the neurons inhibit each other, except it can be weak and strong inhibition, and the arrows correspond to the weak inhibition. So it turns out that you can take seriously this idea of excitatory neurons in a sea of inhibition by building kind of a model within one additional node, which is going to be a global inhibitory node. So the global inhibitory node is going to receive edges from all the nodes in the network, which I think of now as genuine excitatory nodes, and then is going to feed back inhibition to all of them. Okay? And so we have this new equation, which is for the inhibitory node. And now the W matrix, I'm going to generate it in a different way. So I'm going to put a positive value, A sub j. It can depend on the kind of presynaptic neuron. If j goes to I, I'm going to give the same value. So this is like a GCTLN kind of framework. And then actually a 0 when there's no edge. Okay, so this is what everybody always wants. They want a positive weight when there's an excitatory edge and a 0 where there's no edge. Okay, so this network now has that. And the price to pay is you have this global inhibition. So all the nodes then synapse onto this global inhibitory node, which also has some positive weight associated to those excitatory synapses onto the inhibition, and then the inhibition feeds back. I'm just kind of calling it -1. I could put a parameter there, but to simplify the equations, it's just going to feed back a -1 to everybody. And so, this is like a simple network. It's not quite the 3-cycle. And you can see the new EI network is sparse, right? It has a lot of zeros and just positive values where you see edges. I'm not actually drawing in the inhibitory node. It's the same graph. I want to think of the same graphs that I had before, but there is this inhibitory node in the background, and then the matrix, we do add it in, and it's the last row and column. Okay, and for comparison, the GCTLN is going to have 1 dimension less, and is going to be a dense matrix, right? Because you have weak or strong inhibition between every pair of nodes. And so there's actually, by trying to match the fixed points of the EI model with the GCTLN, you can find relatively easily how you map the parameters. Okay, so there's a specific mapping. So if I have epsilon j's and delta j's, that tells me how to choose my AJs and CJs and vice versa. And it's just a very simple linear mapping between them. And I want to compare actually my former student, Caitlin Leinkamper, and her postdoc mentor, Gabe Ocker. They actually, I'll talk a little bit about this at the end, but they have a work where they think about clustered spiking networks and show that the CTLNs can be viewed as mean field reductions of those. And along the way, they build a very similar EI model as well with a slightly different mapping, but it's nearly identical to this. So it's kind of produced in two different ways. Okay, but here's the thing that the fixed points don't tell us how to choose is the time scale of inhibition, right? So we're allowing the time scale of inhibition to be different than the time scale of excitation, and there's nothing telling us how to choose that. Okay, so that's the generalization. And now I want to show you what happens, okay? So by design, the EI network and the GCTLN, if I use this mapping, have exactly the same fixed points, except that the EI one also has the inhibitory node firing at some rate. But they have the same, there's a clean mapping between the fixed points. Do the dynamics look the same, okay? So if you start off, so I'm showing here at the bottom right, the GCTLN dynamics for the 3 cycle, okay? And so you get this nice oscillation that we've seen many times already. Now, when you do the EI network, which is this like sparse network now with genuine excitatory connections and the global inhibition, for tau I, for inhibitory timescale equal to the excitatory one, it's kind of disappointing, right? You actually do not see the 3 cycle oscillation at all. If you zoom in, sorry, I should have made this bigger, but what happens is, so the black is the total excitation, so I'm just adding up the 3 excitatory nodes to get the total population activity for the excitatory nodes, that's the black curve, and the pink is the total inhibition, okay, and it's strong, right? So the inhibition was set up to be strong, and what you see is that the individual nodes synchronize, okay, and then oscillate back and forth with the inhibitory one, okay? So you don't see the graph. You don't see the interesting dynamics, right? You just get this EI oscillation, which I think many people expect when you have a network set up like this. But now what happens when the inhibitory timescale gets faster? So at 0.7, it's not fast enough. But now at 0.5, you start to see the individual nodes separate. You can see that down there. Now go down to 0.4, they separate more. And by the time you're down to like 0.1 in this case, or even 0.2, it looks identical to the GCTLN. Okay, so if the inhibition is faster, and it doesn't have to be 1,000,000 times faster, we don't have to take tau I to 0, right? If we just make it 5 times faster, 10 times faster, suddenly the structure of the underlying excitatory network is totally revealed, right? And you see exactly the same kind of oscillation, even though now the excitatory neurons really are exciting each other, right? And the inhibition is mediated through this global inhibitory node. Not just with the 3 cycle, so you can try other examples. This is a graph we call the 4-sig-U. It has a nice attractor down here. And again, as you make the inhibitory timescale faster, what I've done in this last piece is just remove the pink and black so you can see the individual neuron curves and see how close they are. The transient activity is a little bit different, I have to say, but on the attractor, they're matching. Okay, so this is very exciting. This means that we really can think of this as an EI network and really can think of the graph as capturing the excitatory connections between, say, pyramidal cells, for example. And just, to show even the exotic attractors like the Gaudi, that's the GCTLN, that's the EICTLN, okay? This is the baby chaos ones, they also match, okay? So they all match as long as the inhibition is fast enough, and fast enough appears to be something like 10 times. It might scale with n, right? And we haven't explored that fully. The domination theorems all go through as well, because as I said, by design, the fixed points match between the EI networks and the GCTLNs, and the domination theorems were all about the fixed points. And so now, the previous examples I showed you, we can now do them with EI networks. This blue is zeros, right? And these yellows are positive numbers, and we see the same behavior where the activity converges to the nodes in the reduced network, or to the fixed points in the reduced network. Okay. And even the cyclic chain example, which was complicated, right? And we had all these like rich dynamics. This is actually when I don't identify, I get this like kind of like a sin-fire chain like behavior, except it can be slow. And here's when I identify, and you can see, it's a little busy of the slide, but you can see down here that this is the EI network, and this is the GCTLN that I was showing before, and they look the same. Okay, so all of it goes through, right? So this is very exciting, and then I just kept playing with this. This is a teleportation and addition. So when you do the inhibitory control, it's like a stop sign, and the activity gets trapped right before where the nodes that you inhibited. But when you stimulate a node, you can actually make the sequence reset to the stimulated one, right? So we call it teleportation. So you can do both. It's quite different. So there's not a symmetric situation, stimulating versus inhibiting. Okay. All right, and then finally, I do want to spend just a couple minutes on using this domination reduction idea. So we've used it to build models and with this intuition of like looping around and having this inhibitory control. But we can also now look at connectomes, right? So there's all this connectome data that's come up. And the question is, can domination be useful for connectome analysis? The connectome being the wiring diagrams that people are painstakingly extracting from real brains. And just to get started, because this is all very new, we looked at C. elegans, but let me give you the basic framework. So now with these reductions, you can declare two graphs to be equivalent if they have the same reduction, right? So that the domination reduction sort of gives you an equivalence relation and thus a partition on the space of graphs, where now a bunch of graphs are equivalent to each other. So one of the things that we're looking for is, do connectomes kind of overrepresent certain classes of graphs that are equivalent under domination? Also among the motifs that people find to be overrepresented, so like a lot of people look for small graphical motifs, 3, 4, 5 nodes, small subgraphs that are overrepresented as compared to some model of chance, and we can look at, do the overrepresented motifs, are they more likely to be reducible or irreducible, which motifs are domination equivalent, etc. And then just the easiest question to tackle is like, what about just taking the full network? Can we think about reducing it, and will that tell us something? So we did a really preliminary analysis with my student Joaquin, who's here and presented a poster on this last night, where we looked at C. elegans. Now C. elegans is not so clear who the excitatory inhibitory nodes are, right? But our collaborators did their best to sort of pick out an EE network, right, of like just neurons exciting each other. And this had 143 nodes, so less than the 300 of the full worm. And it reduced to, let's see if I can see this, to just 104 nodes. We actually just fed it through our domination reduction code, which is very simple, and saw that it reduces. So the question then is, did that reduce a lot compared to chance, or a little? And so then Joaquin ran 1 million Erdős-Rényi directed random graphs with the same edge probability that we saw in the C. elegans network. And this is, I just show the numbers here. This is a distribution of what happens. So most of them do not reduce, okay? So if you have a large network and you look at the entire network, it's unlikely, if it's a random network, to get a reduction at all. But even the ones that reduced, I mean, the most reduced one, there was one network that reduced to 137. Okay, but the C. elegans one went all the way down to 104. Okay, so there's something very special about the network that we're seeing coming from a real creature. And also, here are some other controls and looking at reduction sizes of Erdős-Rényi random graphs of different edge probabilities, just to get a sense of how it works. And really, one thing that's clear is the E network from C. elegans is very, very special. Okay, so this is, we're like doing so much more of this, right? So this is now a strategy for looking at all kinds of connectomes, and we're very excited to think about this. Okay, so back to the motivating questions. Just want to highlight the domination property in our case really came out organically from studying the dynamics, right? So there are lots of graph theoretic properties that you can study from, you can pick up a network science book or paper, and there's like all these things you can look for, like the community structure and, the hubs and this and that. And and all of those things are well motivated for some dynamical system, maybe a Markov chain, maybe, but we've found that by looking at a neuroscience-inspired dynamical system, right, these recurrent networks, it leads us to look for different graph structures that we might not have thought of otherwise. Okay, and then, I'm out of time, but I just want to breeze through. So many of you saw, just the bonus advertisement for some other work that's going on in my group. You saw Juliana. Many of you she gave a talk yesterday morning. If you missed it, she has a nice paper out that's in review on using CTLNs to build models of quadruped gates. Caitlin, who I already mentioned, has a really nice new paper using CTLNs as mean field approximations to spiking clustered networks that are probabilistic in their connectivity and obviously in their spiking. So that's really cool. Safan is a graduate student in my group who's presenting a poster tonight, and he's going to talk about this observation and a lot of results that we've gotten so far on the same attractor being present across a large family of TLNs. So there are these, if you look at the moduli space of TLNs, we find that there are large subsets of W matrices that actually have the same dynamic attractor, even though the attractor has interesting structure and is not just a point, right? So it's it's got all this interesting trajectory, but you have large families. And then Safan presented a poster yesterday too, and I just want to highlight his thesis just came out on the archive, and he's been thinking about using this framework to study decision-making and bias in decision-making. So this work is really interesting because one thing that we've found in these networks is that you can preserve exactly the same attractors and alter the basins. So it's like in the network, some of the parameters are controlling the sizes of the basins of attraction, and others are controlling the nature of the attractors themselves. And so he has some interesting work showing how you can think about bias in decision-making networks by using these ideas. Okay, and I just want to thank everyone in my group, and thank you all for staying till the end.
Well, thank you very much for this very interesting talk. I just want to draw a parallel with the term dropout you use and the dropout used in neural network architectures. Do you think that dominance-based dropouts could maybe improve the efficiency of neural network architectures?
Sorry, I could not quite hear because the microphone is a little funny. Improve.
Sorry.
Yeah.
So I was asking, do you think that dominance-based dropout, as you defined, can help improve the efficiency of neural network with the dropout that they use in those architectures?
Yeah, so I mean, on the one hand, right, it's tempting to be like, oh, I can simplify the network. It's really behaving like this reduced network because all these nodes drop out. And then you think, well, then what were those nodes good for, right? And so in a way, this inhibitory control example is showing one of the things they can be good for is they actually can be revealed as being interesting when you control the network so that you alter the domination relationships, right? So when I control that B input, I can kill a domination relationship that was there, and suddenly a node, becomes important again, right? So that's one answer, is that it might be a way of having like many networks really in the same network. The other answer is kind of like along the lines of Safan's work, where those extra nodes, in fact, he looks at sort of directed acyclic graphs, and they all reduce down to the sinks in terms of the attractors. So what is the rest of the DAG doing? And what it's doing is it's shaping the basins, right? So dominated nodes drop out of the attractors, drop out of the fixed points, but might play an important role in shaping the bias and funneling you to one attractor versus another.
I have two over here. Sorry, I have two ridiculous questions. One is there a homology theory that would detect these cycles of like you can't reduce the graph because it's cyclically tied up? And well, that's the first question.
I hope so.
Okay.
So the answer to that question is I hope so. Actually, collaborating with another grad student, Jensi, and Nico Shonsek, who's at Rockefeller, and we are trying to build some kind of topology-like theory, right?
Yeah.
That is going to sort of connect topological features of the graph to topological features of the attractors that we see, and so on. And
then my second ridiculous question is predicated on my ignorance of differential equations. Can I think of a limit cycle in these settings as being an algebraic variety, or are they very distinctly not algebraic?
No, okay. I don't think so. No.
Then I will not ask my more ridiculous question.
That would be too good to be true.
Hi, fantastic talk. Thank you so much. I had a very simple question about the Euclidean, the Erdős-Rényi null model that you used. Have you considered doing things like preserving Euclidean distance or in-degree, out-degree distributions or things like that?
So we're doing the reduction just on the graph, not an embedding of the graph, right? So there's no like distances or anything. It's just the combinatorics of the graph. However, the degree distribution is a good point, and it didn't make it to these slides, but Joaquin has also run similar experiments where you basically take the C. elegans connectome, you can perform shuffles that preserve the degree distribution, both the in and the out degree on the nose, and generate sort of a family of networks that all have the same degree distribution. They also don't reduce as much as the one, so that the reductions are also, they're not quite as bad as the Erdős-Rényi, but the actual C. elegans network is still dramatically outside of the distribution.
I see. Thank you.
But yeah, it's a good idea, and we have done that. Yeah.
Thank you.
Mm-hmm.
Hi, here. Yeah. So thanks for the nice talk. I have some basic questions. Might be not very much. Might be very poor question, but I'm intrigued. So later on, I tried to think that you wanted to use some category theoretical concept, like when you tried to match two graphs, whether their reduced form will be similar or not. So based on that motivation, when you are doing with the group actions working on graphs, should we connect for some symmetrical groups and some subgroups of that, say dihedral groups? The fixed points of the groups will be somewhere similar to the fixed point of the graph. That is my first question. The second one, like when we'll be dealing with some of the edge matrices, so symmetric matrix and sometimes asymmetric matrix, they have different algebraic geometrical manifold structure. Does those manifold somewhere related to the manifold structure of the basin of attraction or in the graph theoretical attraction? And the third one is the dominance. So in the dominance, when we are reducing some of the dominating nodes, can we think about the invariant subspaces in the matrix, where we can get rid of some of the invariant subspace and concentrate on the other invariant subspace where we
Sorry,
can
on the inference of
invariant subspaces, like for example,
invariant subspaces. Yeah, on some level, like the domination reduction is, it's a dimensionality reduction, right? You're literally cutting the dimension down by getting rid of neurons. Yeah, I'm not sure. I'm really sorry. I'm not sure I followed the other questions.
The one other question was like the manifold structure of the matrix. Does it match some way?
The manifold structure of the matrix.
Of the matrix, like for example, symmetric matrix can be divided into submanifolds of upper triangulation or erosion.
So in TLN, symmetric matrices are very special, right? So there is actually a result by Sebastian Sung and Hanleser and Slotine from 20 years ago, that if your matrix is symmetric and it satisfies some other condition, then you're guaranteed to have the dynamics converge to a stable fixed point.
Okay, yeah. So that's,
Right, and so it's really important to get away from symmetry, from symmetric matrices, if you want to study, rhythms and oscillations. So somehow it's like in this model, it's very clear you need asymmetry for rhythms and oscillations. And yeah, so I think the symmetric matrices are in the TLN space, right? That is some low dimensional subset, and it's very special.
and my first one was the fixed point, like the fixed point of some subgroups or groups, will it match with the fixed points of the GCTLN?
Yeah, I think that's a fixed point in a different sense. Yeah, I'm not, maybe we can talk later. I'm not sure I fully know what you're getting at.
You hinted in a sort of previous answer to a question that maybe one of the benefits of having a more general network than the reduced network is that you can apply inhibition to certain parts of the general network and it can reduce to a different sort of network. I'm wondering if in the C. elegans connectome, if you've noticed any of those nodes or if that's something you've been able to search for.
Yeah, I think that's kind of the next step. We're sort of waiting for Joaquin to take his qualifying exams so that we can, which are scheduled very soon. Sorry, Joaquin, for mentioning that. But I kind of sort of back off on doing more analysis for now, because we're really doing it together and it's very fun. And but yeah, so I think we are dying to look in more detail at what are the nodes that got taken away, right? And also in what order, right? So there's some kind of sequence of removal that might be interesting in and of itself. And maybe it's something really obvious, like you have some feed-forward network and you're just kind of removing the nodes according to their sort of topological ordering. But maybe it's more interesting than that. So absolutely, we're very curious. It just gives us a new way of looking at these graphs that other people haven't thought about before. And so anyway, whatever we find might be exciting.
Hi, here. So I'm very interested when you mentioned that the C. elegans network is reduced much more compared to a random network. So I'm wondering if you can relate that. So if we can consider the nodes that got removed, we can consider them as redundant nodes, and whether their presence is related to the robustness of the entire, the dynamic behavior of the entire network.
Yeah, so I think that gets back to something that we've been talking about with other questions too. Maybe they're redundant nodes, and maybe they allow more robustness by introducing some kind of redundancy in the dynamics. I don't know. It could also be that they are funneling activity towards different decisions, right? Or, and so they could be playing a role in the transient activity, right? So just because I can remove them and retain all the attractor structure, right, and all the fixed point structure, doesn't mean that they're not affecting the transient activity. So, but we really need to look more closely. So it's like this is now, we have an opportunity to sort of look more closely at what's happening there.
Well, there were a lot of questions. I'm sure that Carina is happy to answer more questions or have more discussions at the poster session or at the break.